Okay, welcome to this video, and we will start talking about complex numbers and exponential form. Okay, let's start with some consideration, and let's start by representing a complex number on the complex plane. We know that a complex number z can be represented in a complex plane by using a vector. A vector. What if we want to know where is located the complex number that has the same argument of z but has modulus 1? Well, or that is the same. I want to find if this is a circle of a radius 1. Well, this is the representation of a complex number that has the same argument but has a modulus that is 1. Well, this point corresponds to the vector z divided by rho. If rho, remember, rho is the modulus of z. So this is easy to see because, of course, z divided by rho has a modulus which is given by the modulus of z divided rho, but the modulus of z is simply rho. So this is rho over rho, which is 1. So this vector here, I will use the red color. This vector here is the corresponding vector to z, but with the modulus 1. And again, it is straightforward to see that z can be thought of as rho times z divided by rho. Keep in mind this expression, which is, I think, very simple. Okay, I just divided and multiplied by a real number, so this is easy to understand. But why did we this consideration? Well, because we want now to focus on this part of this expression. I want to focus on a complex number with the modulus 1. And we know that each complex number can be mapped by this expression into a complex number with modulus 1. Now, let's start considering a complex number z1, z sub 1 with modulus 1, and a complex number z2 with modulus 1. Z1 is in trigonometric form, can be expressed as the cosine of theta 1 plus j the sine of theta 1, while z2 can be expressed as the cosine of theta 2 plus j times the sine of theta 2. If I make the multiplication z1 times z2, and we just use the usual rules for multiplication in algebra, z1 is given by the cosine of theta 1 plus j the sine of theta 1 times the cosine of theta 2 plus j times the sine of theta 2. And well, if we use the usual algebra rules to make multiplication, what I found here is the cosine of theta 1 times the cosine of theta 2 minus the sine of theta 1 times the sine of theta 2 plus j times the sine of theta 1 cosine of theta 2 plus the sine of theta 2 times the cosine of theta 1. Now, if we remember the rules of the sine, the expression of the sine of the sum of angles for the sine and cosine, we soon see that this is equal to the cosine of theta 1 plus theta 2 plus j times the sine of theta 1 plus theta 2. But this is very interesting because we have seen that multiplying two vectors means find a vector, find a complex number whose argument is the sum of the argument of the two factors. So again, the argument of the multiplication of two complex number is the sum of the arguments of z1 and z2. And this is very similar to what happens when we consider the exponential. For example, we all remember that e raised to a times e raised to b is equal to e raised to a plus b. So we now wonder if there is some representational form for a complex number that makes use of the exponential. One could imagine, for example, that this form could be, for example, e raised to theta. But this is not the right way, and we will soon see why. Let us consider, for example, the imaginary unit j. J is given by the cosine in trigonometric form as the cosine of pi over 2 plus j, the sine of pi over 2. So if I would use this form to represent this number, what I get is that j should be equal to e raised to pi over 2. But e raised to pi over 2 is a real number, so this cannot be the right way to represent a complex number with the Cartesian, with the exponential form. Well, the right way is to use e raised to j theta. This is the right way, okay? This is the right way to represent a complex number using the exponential form. So, for example, z1 is going to be equal to e raised to j theta 1, while z2 is e raised to j theta 2. And remember, this is the right form for a complex number with modulus 1. z1 and z2 are two complex numbers with modulus 1. So what I got in the exponential form is that z1 is equal to e raised to j theta 1. z2 is equal to e raised to j theta 2. Now, this seems to be very comfortable. If, in fact, just to make the multiplication z1 times z2, in this case means just e raised to j theta 1 times e raised to j theta 2. And if we use the usual rules for multiplication of two powers, what I got here is e raised to j theta 1 plus j theta 2, that is the same as e raised to j theta 1 plus theta 2. And this is exactly what we were looking for. I have a representation of a new complex number in which the argument is the sum of the arguments of the complex number that are the factors of the multiplication. However, this position that seems very obvious should be validated, should be checked out against every property of the exponential. Right now, we still don't have all the notions, all the knowledge that allow us to verify all the properties. So we will do this later in this course. For the moment, just accept this as the right representation in exponential form. But if we go back to the first position that we used, remember this position, we said before that at the starting of the lesson that each complex number z can be represented by this expression by using rho times z over rho, while z over rho is a complex number of modulus 1. So this means that for each complex number z, this can be written as rho times z over rho, but z over rho is a complex number with modulus 1, so it can be written as rho e raised to j theta. And this is what we call the exponential form of a complex number. This is what we call the exponential form of a complex number. Yeah. If we want now to use to map this exponential form into the trigonometric form, well, this is straightforward to do, because z can be also written, the trigonometric form is rho times the cosine of theta plus j the sine of theta. So we could put all together this in one single expression, that is rho e to j theta is equal to rho times the cosine of theta plus j the sine of theta. That is, of course, the same as to say that e raised to j theta is equal to the cosine of theta plus j the sine of theta. And this is the Euler's formula, which states the correspondence between the exponential form and the trigonometric form of a complex number. This is a fundamental property, and we will be using this formula a lot of times because it is really very convenient for our kind of application. Now let's now try to understand why it is so important to use the exponential form for complex numbers. But we have already seen that it is very easy to make multiplication. It just need to add the arguments. But we have been using this for a complex number with modulus 1. What to do if we have a generalized exponential form? For example, if we have, I'm sorry, this is not the right color. Okay, z1 is rho 1 e raised to j theta 1, while z2 is rho 2 e raised to j theta 2. Well, the multiplication z1 times z2 is just given by rho 1 e raised to j theta 1 times rho 2 e raised to j theta 2, which is rho 1 rho 2 e to j theta 1 plus theta 2. So the multiplication here comes very simply, because it just what we must do is just multiply the moduli of each complex vector and adding the arguments of each complex vector. While if we have to make the ratio of two complex numbers, z2 over z2, this is equal to rho 1 e j theta 1 over rho 2 e to the j theta 2, and this is as to say rho 1 over rho 2 e to j theta 1 minus theta 2, and again it's very simple. And also it is straightforward to make the power. Suppose that we want to find the nth power of a given number z given in exponential form rho e to the j theta. Well, the nth power z raised to n, this means rho e to j theta to the n. But this, just using the usual rules for the powers, I get rho to the n times e to j n theta. So what comes out is that if I want to find the nth power of a complex number, and what I need to do is raise to the n the modulus and multiply by n the argument. And this is a very simple way, also compared with the difficult calculus that we had to do if we use the trigonometric or the Cartesian form. Okay, that's all for now. Next time we will do some more examples using the exponential form, and we will see how convenient can be the Euler's formula, the exponential form of a complex number to make complex calculation. Thank you, and let us see the next time.